problems from Brazil to bring here.
Yeah, I'm going to check out Brazil. So there was one session where I did like the Brazilian Olympic revenge, but yeah, like you said, it was like so hard that we couldn't solve any because those are like really advanced problems for like
Yeah.
and stuff.
Yeah, the teachers did the problems there.
Yeah. But yeah, maybe just their normal Olympiad or their team selection tests, I could do some more problems for it.
Yeah, nice.
All right, so I'm going to draw the in circle of triangle ABC. And then let me call it I instead of D. So D, E, and F are the points of tangency. M is the midpoint of EF. So obviously it's where EF and AI intersect. Might as well draw that. The circumcircle of DMF, just because I'm OCD, I'm going to fix the spelling of that. The circum, otherwise it would just bug me. Okay, so the circumcircle of DMF intersects AB at L. And the circumcircle of DME intersects AC at K. Okay, let's call it K and L. And we want to show the circumcircle of AKL is tangent to BC. That's kind of interesting. Let's check it out. So AKL almost looks isosceles. It looks like they're tangent at point D. So we kind of cheated with GeoGebra a little bit here. GeoGebra is kind of giving away a lot of the idea. But is AK equal to AL? No, not necessarily. So it's not an isosceles triangle, but can we show AKLD is cyclic and also that it's tangent? So that would mean, I mean, if it was tangent, we'd have BD squared as BK times BA.
Can you draw a line KL?
Can I draw? Yeah. So here's KL. It doesn't pass through I.
Is BKLC cyclic?
Maybe, let's see. BKLC. No.
No, but is it tangent? Like the circle is tangent to the side AC?
I might think that, but on this side, it's clear it's not. Oh, actually,
yeah.
maybe. Yeah, no, because it's not symmetrical, basically what you're saying. So.
Oh, no.
No, but it's close. Let's see. ADLK is cyclic by an angle chase. Okay, so I guess I'll kind of take your word for it that it's not hard to show that ADLK is cyclic. Find angle IDK or LDK as MDK plus MDL. Okay, so and then that, yeah, okay, I see how that would do that. Okay, so we know ADLK is cyclic.
Can you explain why is it cyclic? I didn't understand.
So basically angle MDK, so angle LDK is angle MDK plus angle MDL, right?
Yeah.
An angle MDK is the same as MFA because of the cyclic quadrilateral.
Nice.
An angle MDL is the same as angle MEA.
Yeah.
And So those two angles add up to 180 minus angle A. And so, yeah, so that has to be cyclic. Now we just
really nice.
Yeah, it is really nice. And now we just have to show that that cyclic quadrilateral is tangent to BC. Maybe it's obvious. Also, MD is the angle bisector of LBK. Yeah, because AF is equal to AE. They're both tangents to the end circle. So angle MDK is equal to angle MFA. So yeah, so basically MD has to be an angle bisector of KBL. That's an interesting observation.
Another thing that we could notice is that the center of the cyclic quadrilateral should be on like sideline ID.
Is M the center of that circle?
I don't know, but it should be on side ID if we use the fact that it's tangent on point D here.
Yeah, I see what you're saying. The circumcenter, so I'm going to draw the circle, which we don't know is tangent yet. But if I go here, I'll say O is center of P. Yeah, basically O would have to be on ID if those were actually tangent. All right. So yeah, no, M isn't the center of that big circle. Let's see. How would we show that this circle is indeed tangent? Can we show angle KDB is equal to angle KLB or something like that? KLB? So AM is an angle bisector, and DM is also an angle bisector. It kind of feels a little bit like harmonic quadrilaterals, but it's not. It's like DM.
What is a harmonic quadrilateral?
Harmonic quadrilaterals, it's hard to describe without. So here's one way that you can describe what a harmonic quadrilateral is without having a no projective geometry. So basically, if let's say you have I'll just draw this very quickly just to teach you. But here's one definition. But what's really cool about harmonic quadrilaterals is there's so many equivalences that you can, if you know it with one definition, then you can use like all the other definitions. So like here, so GHOJ is a harmonic quadrilateral because if I draw the tangents at H and J and they meet at N, then GO passes through N. So if
that's definitely related to Cymedian points.
Like, yeah, it's very related to Cymedians. So yeah, GHOJ is harmonic. And then not only that, I could take these two tangents at O and G, and then HJ has to pass through that. But there's even more stuff we can say. Not only can we say that, there's alternative definitions. So it also happens to be the case that GH times OJ is GJ times OH. So that's another definition. And then another definition is that if you take the angle bisector of these two, they meet on HJ.
No way, that's really nice. I didn't know this.
And there's even more stuff that you can conclude.
It's very useful, like very useful.
Yeah, definitely. So perhaps draw DE. I'm going back to I3435 suggestion. I think this problem is about power of a point. Anmol asks, are these three segments concurrent? Which three segments are you thinking of, Anmol? BC, EF, and KL. They might be. It might. No, I don't think so. But it's an interesting idea. If we could look at the incircle, the circumcircles of FMDK and ALDK and do radical axis stuff. But those three circles all pass through point B.
Oh yeah, that's right.
Yeah, it's hard to do, but let's see. So we just need to show that that circle is tangent, AKDL. I3435 said power of a point, possibly. We want to show KL bisects the segment between D and EF intersect BC. That would be interesting. So kind of going back to Anmol's, what he was sort of thinking. I'm guessing, but no, I don't think KL bisects that segment. Let's see. Yeah, maybe you were thinking something with like projected geometry. Can we prove that ADC is equal to DME? Possibly. ADC is 103.5. And DME is 103.5. If that's true, we can just use an angle chase. Interesting. So DM is like a Cymedian, right? It's a Cymedian in the triangle DEF. I feel like there has to be a nice proof of that angle DME is equal to angle ADC. Yeah, that feels like it just has to have a, like, I'm surprised I don't see right away why that's true, because it just feels like it has to be. Draw line AD. Since AD is the Cymedian of DEF. Yes. Okay, so basically angle DME is equal to angle FDA. Let's see. So what did Anmol say? Anmol said we want to show that ADC is equal to DME. So ADC is equal to GFD. Yeah, it has to, it's true by, I'm trying to think how to say this. So, but basically, yeah, so, okay, yeah, I called it G, but yeah. So I can show what Anmol said. Now I'm just trying to think. So if we can show angle GDC is equal to angle GFD, does that solve it? Yes. I just have a bunch of stuff going on in my head right now. Okay. All right. So let me just think about the best way to say this. Because angle CDG is equal to angle DFG, which is equal to angle DME. And that's, yeah, so, all right, so I'm going to write this all out. It makes some room here. Okay. Maybe move the diagram a little bit just to make more room for the text. We can't use CDG is equal to DFG. We can use that fact because we know the in circle is tangent. Yeah. So let me erase the stuff that I sort of discovered throughout the problem and start from scratch. And now I will just write it from the beginning for the viewers on YouTube. Okay, so M is the midpoint of the F. The circumcircles intersect at L and K. Prove that the circumcircle. Okay, so first I want to show AKDL is cyclic, so I'm going to do that. Sorry, my yeah, the text covers up the figure, but so we have KDL is KDM plus MDL. Which is equal to angle AFE plus angle AEF, which is 180 minus angle A. Okay. So by that angle chase, we know that AKDL is cyclic. All right.
Just a curiosity, like the circumcircles of the triangles BKD and CLD are tangent.
Oh, really? That's interesting.
I think so.
Let me check it. Yeah, they certainly look tangent. Yeah, I feel like that has to be true. Interesting. I'll have to check it out after. Okay, so AKDL is cyclic. So I'm not going to draw it in yet because I don't want it to look tangent to point D yet, because that's what we're trying to prove. And now we can do the stuff with Cymedians. So by the Cymedian theorem, angle EDM is equal to angle FDA. And that's in my video 52.
Yeah, I don't know this theorem. I'll see video 52.
Oh, did you say you do know it?
Yeah, I don't know it.
Yeah. And then we also have so EDM is FDA, and we want to show also that MED is equal to what was I just doing? We want to show MED is equal to FAD. Or no. So I'll write this. I'll write it like this. So angle EMD is 180 minus angle FMD. Just leave it, which is 180 minus BFD. Okay, so EMD and AFD are similar, and that's kind of like a well-known fact. I'm just proving it here. And so angle FAD is equal to angle DEF or DEM. Actually, so let me try to just think about what I was trying to prove here. So I want to show angle ADC is equal to angle AFD. No, I'm sorry. Angle AKD. EMD and AFD.
What are you trying to show? Like what?
Oh, I'm sorry. I forgot to draw in the intersection point. My bad. No. Yeah, let's call this point G. No, yeah, I'm sorry. EDG is, yeah, no, it is a mess. Let me go back. Instead of A, it should be AD. Oh yeah, I'm sorry. So we want to draw the intersection of AD with the in circle. We have, yeah, EMD is similar. We want to show EMD is similar to GFD. And that, okay, so. All right. And then also angle FGD is equal to angle so FGD is similar to MED. All right. And so ultimately I wanted to show GFD was equal to ADC, but we have GFD is equal to EMD. I'm trying to think about this, and also GFD is equal to ADC. So hold on just a sec. Yeah, we want to show those are equal to AKD. So just doing this in my head. So we have FKD. Is it obvious that FKD is equal to DME? Yes, because of cyclic quadrilaterals. Okay, so we have FKD. So I'm going to write this. So AKD is FKD is EMD, which from up here, EMD is equal to GDC, or is equal to GFD. And GFD is equal to GDC. So I'm not sure if this is the shortest way to do it, but if AKD is equal to, I'll write it out like this. If AKD is equal to ADC, then that means BC is tangent to the circle of AKL. So I don't know if I did this the fastest way or there's a better way to do it. Let me just think through this one more time. Okay, so, but I believe this solves the problem. So we have angle EDM is equal to angle FDA, which is FDG. Then also FGD is equal to FED is equal to MED. So those two triangles are similar. And so then we can conclude with an angle chase. We have angle AKD is FKD is EMD. EMD is GFD, since those triangles are similar. GFD is GDC, which is ADC. I think that might be the shortest way to do it. What do you guys think? But yeah, I think this might just be the fastest way to do it.
I don't even know the Cymedian theorem, so.
Yeah, so yeah, the Cymedian theorem, all it says is like in that configuration I had before, so I could just draw it very quickly now. But yeah, it's very nice. It just says I'm going to draw the tangents at H and N. It just says that angle NO, whoops, angle N, angle NJO is equal to angle HJP. That's all it says. So O is the midpoint. O is the midpoint of HN. The Cymedian theorem just says angle NJO is equal to angle HJP. So yeah, it's a really simple theorem, but it's very useful.
HJP equals what?
Equals NJO.
But that's what's the definition of the Cymedian, isn't it?
Well, usually I think of the Cymedian as defined as being like the reflection of JO, but like I usually think of the Cymedian as being the defined to be like where angle NJO is equal to angle HJP, and then you have to prove that the Cymedian passes through point P, right? So I guess there's something to prove, right?
Oh, nice, understood. Yeah.
Yeah.
I thought, yeah, understood.
Yeah, I guess you could kind of use either one as the definition. Like most people, they define it to be where NJO is like equal to HJP. It's like the whole line JP, right? And then you have to prove that it passes through the two tangents. So yeah, it's a pretty useful property. All right, so I'm going to move on to the next problem. This one is from Greece. Now, what's really fun,
this sounds a nice problem. Yeah.
What's really interesting about Greece is they always say let O be the circumcenter, even if they don't use it. And also they always say let AB be less than BC, less than CA, even if you don't need that. So every problem they do is like that, which is kind of funny. But let's see. So they want AB to be less. They want like AB to be the longest side. So no, I'm sorry, the shortest side. So maybe something like that. Okay, but it probably won't be used. So D is the center of the minor arc AB. So let's see, I'm just going to draw it like this for now, but it might be better if A, B, and C are like permuted. Where's my perpendicular bisector? So D is the center of that. AD intersects BC at E. And the circumcircle of BDE intersects AB at Z. So yeah, for those of you I don't know, usually I do this for like 3 hours, so I'll probably stop in about an hour. But we still have a while to go, but you're free to leave whenever you want. So don't feel bad about leaving if you have to. Okay, the circumcircle of ADZ intersects AC at H. And we want to show that BE is equal to AH. All right. Let's hide a couple things here. How do we show BE is equal to AH? So we have BE times EC is ED times EA. Feels like it's got to be just power to point in some way. Just checking you're still on. Okay. All right.
Probably just draw DB for viewing.
Yeah. So yeah, DB is equal to DA. So obviously D lies on the angle bisector. Let's see. I feel like there's probably some congruent. Are triangles DEB and ADH congruent? They look like they might be. Yeah, I think they would have to be, right? Is it that easy? Wait. Yeah. ADH and EDB and AD is equal. Yeah, that solves it. All right, we already solved it. This is a really quick one. So we want to show ADH and DBE are congruent, and we can try to use side angle side, or actually angle side angle is better. So so clearly we have DA equals DB. And then also angle DBE is equal to angle DAC is equal to angle DAH. And then can we show one more angles equal? It probably shouldn't be too hard. So we have angle EVB is equal to angle ACB. let's see. How do I get one more angle? So angle EDB, I want to show is equal to angle ADH. Is that obvious? Let's see. Oh, well, I can show angle AHD is AZD is DEB. Okay, and that does it. So let me AHD, AZD, DEB. All right, so basically that means that DBE is similar to DAH. And so dA equals dB means that they're congruent. And so BE is equal to AH. This is a nice, easy one. Help us build confidence. All right. If no one has any questions, I will move to the next one.
Yeah, that's quite easy. This one.
Yeah. All right. Let's see how hard this one is. So this is from the 2023 team selection test. So yeah, they always say inscribe it in a circle with center O and radius R, but they do actually use O in the problem. So I will give them credit for that. Let BD be a diameter. So yeah, I don't know if it would be better with B at the top, but I will just do it like this for now. BD is a diameter, so often I'll do diameters like this. So those are both right angles there. And then the midpoint of OD is the center. So all right. The perpendicular bisector of BD, so that passes through O, it intersects AC at M and AB at N. So we have to extend AB. So it intersects line AC at M and line AB at N. Okay. Whoops. Oh, whoops. What am I doing? Oh, it should be this point here. This is M. That's N. You don't even really need point E. I guess I'll just leave it there because why not? Line ND intersects the circle at T. So by symmetry, T has to be the reflection of A over ON. S is the intersection of OCM and OAB. That's kind of random. And it looks like n, is n necessarily on that? Yes, n has to be on, so NaOD is cyclic. So GeoGebra kind of gave that away, although I don't think it was super hard. It's probably super hard to see. And we want to show AD, OS, and CT are concurrent. Feels like the radical axis theorem, doesn't it? Is it just radical axis? Let's see. Is it literally just the radical axis theorem? Wait, what's going on? Yeah, once we show NaOD is cyclic, it's the radical axis theorem. These problems are so silly. Oh my goodness. Wow. Okay. I'm gonna write.
How did you show that the quadrilateral was cyclic?
Yeah, so since BD is a diameter, angle BAD is 90 degrees. So angle NAD has to be 90 degrees, right? And also angle NOD is 90 degrees because basically by symmetry, like NO is the perpendicular bisector of BD. So NOD has to be 90. And so if NAD is 90 and NOD is 90, then NaOD is cyclic.
Really, really easy. Yeah.
Yeah, I don't even know if I feel like writing this up, but just to prove to my viewers on YouTube that I actually solved this, I'll do it very quickly.
But very nice, very nice.
Yeah.
But
So,
it's just like the radical center.
yeah, it appeared in, yeah, it was a 2020 team selection test. Okay, so so yeah, it even says BD is a diameter. So angle BA, so BD is a diameter. And so also N lies on the perpendicular bisector of BC. So NaOD is cyclic. Oops. So then we can draw that in. And then, so then S is this intersection point right here. So by the radical axis theorem, OS, CT, and AD concur. But to be fair, GeoGebra made it slightly easier because I could just see right away that NaOD was cyclic, but I think I still would have seen it pretty quickly even without GeoGebra. All right, so I will now move on to the next one, which is also from Greece. Let's see, it might also be kind of easy. I can't guarantee that it isn't, but let's see. So, so we draw the perpendicular bisector of angle. So yeah, we draw the angle bisector AD. And then the perpendicular bisector Oh, we want to draw the circumcircle too. This looks very familiar. Like, I feel like there's like maybe a YouTube video I did where where I did the perpendicular bisector of AB. So this is K. K lies on the arc AB. L lies on the arc AC. The circle through K with radius KA intersects the circle again at T. Yeah, KA has to equal KD because K is on the perpendicular bisector. So we could call this point T. And we do the same thing on the other side. And that intersects it at F. We want to show angle BAP is equal to angle CAS. Okay. So basically, we want to show AT and AS are orthogonal. I would try using the orthogonal line lemma, but I'm guessing there's likely an easier solution. So it suffices to prove ST is parallel to BC. Yes. K, D, and S are collinear, and T, D, and L are collinear, is what that looks true. So maybe that just solves it pretty quickly. Let me let's see. So I'm sure this is an angle chase to show those are collinear. That might also be an angle chase. Let's see. And then, yeah, so we want to show like arc. Yeah, right now I'm just taking your word for it that an angle chase
is D the, what is D?
D is the angle bisector from A to BC.
Oh, nice.
So we want to show BAP is equal to CAS.
We could prove that TAD equals DAS.
Yeah, we could do that too. Yeah, we could show that TAD is equal to DAS. That might be an easier way to think about it. Which is also the same as showing TKD is equal to DLS. And
it's true
and that's true.
Yeah.
So yeah, it really
why is it the same thing as proving the other one?
If we show TAD is equal to SAD. So we want to show TAD is equal to SAD, but those are each half of TKD and SLD, right?
Why? Why are they half?
Because angle TAD, if you look at this circle, K is the center of the circle, right?
K is the center, yeah.
So yeah, TAD is half of TKD. But we still have to show what I3435 said, which is that KD and S are collinear. And Arabian math says KDL is tangent to BC by angle chasing. Sounds like operations with arcs might crack it too. Yeah, how do we show TD and L are collinear and KD and S are collinear? That would solve it by what I said. So angle TLK is the same as angle TAK. I'm just trying to think. We want to show TLK is equal to DLK, right? So DLK is half of DLA, which is DSA. Just trying to think here. So is it obvious that, how do we know KDL is tangent to BC? Because I see that would solve it, I feel like. KL passes through the center of the A Apollonius circle. So, okay, I believe that. So, how, yeah, how do we angle chase that? What, let me, oh, that's the circle with center K and radius KA. So basically the circle centered at C, centered at K and passing through A. Yeah, it's still not that obvious in my head how to solve this, but if some of you can write the angle chase in more detail, then I could write it out. So I agree that let's see, how do we know KDS and LDT are collinear? Maybe there's something I'm missing. Is it? So I guess like we want to show KDA plus SDA is 180, right? So KDA is KAD, SDA, we could find it in terms of SLA. Which we could find, Is it obvious that KDS and TDL are collinear? Let me look at, so Arabian math, you mentioned that KL passes through the center of the A Apollonius circle, and I see why that's true. Whoops, which is this point right here. How does that help solve it? So ED squared is EB times EC. Okay. Yeah, if we can prove KD and S are collinear and TD and L are collinear, that would solve the problem by stuff that I realized before. Hold on one sec, guys. I'll be right back. All right. Angle ADK is KAD. Angle SDA is half of angle ALS. Okay. So SDA, it's like 180 minus an angle that's half of ALS, right? So it's but if you use directed angles, then yes, SDA is half of ALS, right?
I think it's I think I got it. Like you know, like KL is the angle bisector of AKD, right? So
Yeah.
you only have to prove that arc AL is the same as arc SL.
Yeah. Oh, that's so. Now I feel so silly now that you said that. It's so obvious. Okay. All right. So now we can write up the solution. So since LA is equal to LS, L is the midpoint of arc AS. So KL is the angle bisector of AKS. And we also know KL is the angle bisector of AKD. So that pretty much solves it. Yeah, I'm getting old. It's now taking me a long time to see those kind of things. But yeah, okay. So, all right. Okay, so that means AL is the angle bisector of AKS. And we also know KL is the angle bisector of AKD because all right. And so KD and S are collinear. And then similarly, TD and L are collinear. All right. And once we know that, yes. And then basically that means the triangles KDP and LDC have to be similar. because they're both isosceles. So yeah, so those two triangles, they're both isosceles, and they both share an angle, so they have to be similar. Oops. Let me try to move it to a new line. Huh. Maybe that'll do it. Whoa. Interesting. Doing a little law tech learning here. Screw it. I'll just do this. Here we go. And so then that means that angle TAD is half of angle TKD, which is half of angle TLS, which is half of angle DLS. Let's hope this all fits, which is angle DAS. Okay. This might be better on two separate lines, but let's see. I think that's fine. It'll just overlap the figure. And then since BAD equals CAD, and that solves the problem, because that means that angle BAT is equal to angle CAS. All right. Move on to the next problem. All right. There we go. Another one from Greece. So we have a triangle, triangle ABC. This one involves X circles. So maybe it'll be harder, maybe not. We'll see. The X circle CA, it touches, let's see. How do I do rays? A ray. It's another ray. All right, so we want to draw the X circle. Here's usually how I like to do the X circle. You can kind of use the in-center, X-center lemma. So the X circle, this is the center of it. And if let's shrink things a little bit. That's the X center. That's the in center. Here we have our X circle. All right. They're saying I is the center. Usually I is the in center, but they're saying that they want I to be the X center. So I'll have to go along with what they say. It touches BC at D.
I think the person that created this problem doesn't have like a mind and a heart to feel.
Oh, yeah.
Like, he called I the accent center. Like, oh my
They're
god.
trying to mess with us. Yeah.
Yeah.
Tangent to AC at E. Z. Why would it be tangent to AC at Z? Yeah, I feel like they're really trying to mess with us here, right?
Yeah. Like they will call the circumcenter H.
Yeah. All right. AI. It's so hard not thinking of it as the incenter. AI cuts C at point M. So yeah, maybe that's part of the challenge of this problem is having to work with different letters. The circumcenter should be C, obviously.
Yeah.
Yeah. Next level is just plain Greek letters.
Yeah.
Okay. And the circumcircle of AZE, which passes through I. This is funny. So the circumcircle of AZE obviously passes through I. Is it tangent to? Yeah, it is tangent to this circle. I believe centered at M, right? Because they have the same the diameters are collinear. So AI, it cuts that circle at K, which is, wait, what? So K is I? Wait, I'm so confused. AI, it cuts one of the circles at M, and it cuts the circumcircle. What is the circumcircle C1? Yeah, maybe I didn't copy this right, or maybe I have to go look at AI cuts ABC at K.
Well, it says it's the
Okay.
circumcircle of AZE.
AI cuts C. Wait. Just line, so AI cuts ABC at M, and AI cuts. Oh, the circle with diameter AI, maybe they, wait, AZE and ABC. Okay, so this is K, I guess. Oh, the yeah, no, I'm just getting all confused. My bad. So this is K, this sort of intersection point. And the circumcircle of OKM, so here we do need point O. So that's O. All right. So draw the circumcircle of this isosceles triangle, and it cuts C1 at a point N. And we want to show ANKI. They intersect on the circle. So let's check it out. That looks like it's true. All right, so I'm going to start hiding some stuff. Should I? I'll just leave segment AI and okay. This is interesting. Complicated diagram. Doesn't necessarily mean the problem is hard, but the diagram is complicated. Reminds me of a last Thursday's blog post. Oh yeah. Let's see. I'm guessing, do you mean like the Sharky Devil blog post? This is just plain root BC inversion. All right, so let's try, so root BC inversion, it swaps the incenter and the excenter, right? See if, try to teach me a little bit here. So I'm learning from you guys. So how do we apply, show me how we apply root BC inversion to solve the problem. So I know I and F are swapped, right? B and C are swapped. How, let's see.
I don't actually know inversion because like I'm junior yet, but I don't know inversion.
I don't know it that well myself. So line BC and the circumcircle of first I'm going to try to figure it out from I-3435 in Arabian math, and then I'll try to explain it to you. So line BC and the circumcircle of ABC are swapped, right? Are A, O, and N collinear? Yes. Oh yeah, root BC inversion. If you go on AOPS and you search geometry, it's all over the place. Like everyone is using this root BC inversion. So it's like what you do is you so you've heard of normal inversion, I'm guessing, right? But it's like you look at a circle centered at A with radius square root of AB times square root of AC. Okay, the concurrency point is the A antipode. Is it clear why that's true? Let's see. You don't think we need root BC inversion? All right, maybe I'll do a video on root BC inversion sometime later. But yeah, if we don't need it, I'll try to do, I guess, a solution without it. Okay, so let's see. Simple angle chasing works too, in general. If A prime is the antipode, then I, A prime, and K. Yeah, so I'm going to let A prime be the antipode. So I'm going to reflect A about O. And so then you're saying I, A prime, and K are collinear because those are both 90 degrees. That's hold on a sec. Is that? So A prime KI. Wait, why is A prime KI 90 degrees? Anything about this? Oh, because AI is a diameter. Well, yeah, because A prime KI is AEI is 90. So yeah. So K, A prime, and I are collinear, right? And yeah, I3435 just said it in the chat. So all right, so K, A prime, and I are collinear. Can we show that those A prime, and N are collinear? That would solve the problem. Oh, so basically in the chat, I3435 mentioned that angle AKI is equal to angle AEI, which is 90 degrees. So if angle AKI is 90 degrees, and then also angle AKA prime is 90 degrees, because we said AA prime is diameter. We defined A prime that way. And so that's how we know that K, A prime, and I are collinear. So the next step is showing that A prime, and N are collinear. Maybe that's some radical axis trick. I don't know. Or maybe not. Let's see. So I guess we kind of want to show. Let's see, is AN the radical axis of some pairs of circles? I don't know. can let n prime be AO intersect the circumcircle of AZ, and then show OKMN prime is cyclic. All right, sounds like a good idea. AO. Okay. I'll just try that out for now. So if we call this n prime, so MA prime NI is cyclic. MA prime N prime I. That's probably an angle chase, I'm guessing. So because angle AMA prime is 90 and AN prime I is 90. So yeah, so that's the cyclic quad. We want to show that guy's cyclic. We're actually done here. How are we finished? Let's see. Okay, so angle MNO is equal MNO. I'm going to say M prime here is equal to wait, but how do we know that? Are you using N or N prime to solve the problem? So I'll just go back a couple steps to see, because I think you're using N as it was originally. So MNO is equal to M N prime. Okay. So how do we know MNO is equal? How do we know MN prime O is equal to MN prime A prime? Like that very first equality you said in the chat. How do we know that that's true? But oh, so wait, so we defined N prime to be the intersection of AA prime, and I got confused about what we were trying to prove and what we know. Okay, so we defined N prime that way, and then we have MN prime O is equal to MN prime A prime is MIA prime is MIK, is AIK, is AKC. So and then AKC is A N prime C. So AIK is equal to AK. So we want to show OMKN prime is cyclic. And we're trying to do that by showing M. Okay, I think I see what you're saying. Okay. Let me work this out. Okay, so I'm going to start writing it up. This might be your last problem, or we might have time for one more. I'll see. But I think I see. Okay, so I'm going to delete some of the extra stuff I've added. Let's see. So did I ever use this circle? I don't know if I ever. Well, yeah, because I said A prime is the antipode of A. So let's see. So let's see. First, we showed that K, A prime, and I were collinear, right? So yeah. Is A prime the incenter of M N prime K? It might be. Yes, it looks like it. Yeah, because it has to be, because we said K, A prime, and I were collinear. Yeah. Okay, so let me go back a few steps. So so let A prime be a diameter of C. And then let A prime meet the AZE at N prime. Is it a USA TST problem? I haven't seen it, but maybe it is. Okay, so and then so first we can show K, A, and I are collinear. So all right. So K, A prime, and I are collinear. We can draw that in. It's also not hard to see that M, A prime, N prime, I is cyclic, so I'm going to do that right now. So it's angle AN prime I, which is equal to angle ANI. Or maybe I'll write it like this, just to make things really easy. So A prime MIN is cyclic. So we can draw that circle. And now we can do an angle chase. So we want to show K, O, M, and N prime are cyclic. So we have angle M, N prime, A prime. I'm going to copy sort of the what was said in the chat. So MNO is equal to MN. Yeah, so we have I'll just change this to be a prime here so people don't get confused. Forgot to put my primes in. All right, see you next Sunday, Arabian Map. Yeah, so this will be the last problem we do. So I'm just going to finish writing it up. So we have angle MN prime O is equal to angle MN prime A prime, which is equal to angle MI A prime, which is equal to angle AIK. Which is, let's see, angle AIK. All right, see you, Anmol. Thanks for joining. Yeah, see you, Enrique. So yeah, it won't be more than 15 more minutes, but yeah, thanks everyone for joining. All right, so let's just finish this up. So we want to show angle AIK is equal to angle MKO. And that should probably just be a simple angle chase, I would guess. So MKO we can write in terms of MOK, which is half of MAK. Oh yeah, definitely. So yeah, see you next time. So we want to show MN prime KO is cyclic. And so let's see. Angle AIK.
Yeah, you want to show that that's equal to OKM, right?
Yeah. And I think maybe I just have to draw like the midpoint of AI because AI I think is a diameter of this bigger circle. So angle AIK is, I don't know if that makes things harder actually. Do you see
You
how
could
to
draw like AK probably like.
So AIK is 90 minus, oh yeah, that's it. AIK is 90 minus IAK. And then that's 90 minus MAK. Let's see. We want to show it's equal to MKO, right? So is 90 minus MAK equal to MKO? So this is 90 minus half of MOK. And that is equal to angle, that should solve it. That's equal to angle MKO because MKO is isosceles. So that means that OMN prime K is cyclic. And so that means that N prime equals N. And then that solves the problem. So then AN and KI intersect on C. All right, so I'm going to stop here, but I think we had a really good session this time. We got through a lot of problems.
This one was a little bit more difficult than the others from Greece.
Or did you say this one was a little more? Oh, this last problem was harder than the other Greece problems. Yeah.
Yes.
I definitely agree. So yeah, I'm glad we ended on maybe a more challenging problem. But yeah, I was really happy that we got through a lot this time. This is pretty fun. So yeah, thanks everyone for joining.
Thanks so much. Too.
Absolutely. And yeah, feel free to follow up on Discord. But I will see you all next time. So have a good one.
Yeah, I think my favorite problem was the line MN tangent to the circle.
The very first one. Yeah, I like that one also a lot. I think that might have been my favorite one. So I'll stop recording now, but for everyone on YouTube who's watching, thanks. So yeah, if you liked it, give it a thumbs up and subscribe to my channel.